In this video, we are going to look at how to predict the modes of nuclear decay. Another way to look at that is if you have an unstable nuclide, which type of nuclear reaction will the unstable nuclide undergo? So when we look at this, we have to determine what type of nuclide we have. So we have to look at the nuclide type, what that means, and then look at the mode of decay. So when you have a nuclide that is neutron rich, that means it's going to have a high N to Z ratio. And if it has a high N to Z ratio, it means that it has too many neutrons, and so it will undergo a beta decay reaction. And that is where you have a neutron that gets converted to a proton, and it lowers the N to Z ratio. If you have a nuclide that is proton rich, that means that the N to Z ratio is too low, then you're going to have a beta emission. And if you recall, that takes a proton and converts it into a neutron, and that will increase your N to Z ratio. Now, keep in mind that electron capture gives the same results as the beta emission, so it will work as well. And then finally, we have heavy nuclides. And so if you have a heavy nuclide, your Z is greater than 83, and it will always undergo alpha decay. And that is because that's the best way to reduce both the protons and neutrons. It's a way to just get rid of a bunch of stuff. So if we look at some of the examples that we saw in the previous video about nuclear stability, we had cesium-110, and it is proton rich. So since it is proton rich, it is going to undergo beta emission. So if I do my chemical reaction, we're going to have cesium-110. Whoops. There's cesium. And it is going to emit a positron. And then it will keep the mass number the same, but the number of neutrons is going to change to 54, and we have xenon. Now keep in mind that you're not always going to make a stable nuclide. This is where you can have another reaction take place. The other example that we looked at was neon 20 or argon 42. And we said that argon 42 was unstable. And in this case, it is going to be neutron rich. So that means it's going to undergo beta decay. And when we look at the nuclear reaction for that, we'll start off with argon 42. It will emit a beta particle. Now my number on the top stays the same. My number on the bottom changes to 19, and that is the atomic number for potassium. So let's look at a couple more examples. So predict the mode of decay for the following radioactive nuclides. So we can look at boron 12, uranium 234, arsenic 81, and then finally lanthanide 127. So let's start off by looking at boron. So with boron, it has 5 protons and the atomic mass is 10.81. So if we look at the nuclide's mass value of 12, that is significantly higher than the atomic mass. So that tells us that it is neutron rich. So also, if you calculate the N to Z ratio, that will give you a really high N to Z ratio, too high for such a small atom. So boron 12 is neutron rich. So that means it will undergo beta decay. So I'm going to start off with my boron 12. I'm going to emit a beta particle. The number on the top will stay the same. The number on the bottom is going to become 6, and carbon belongs to 6. So this will be the nuclear reaction that boron 12 will undergo. Now, if we look at the next one, uranium has 92 protons. So my Z is greater than 83. So this would be a heavy nuclide. And remember, if we have a heavy nuclide, it will undergo alpha decay. So it is going to start off with my original nuclide. It will emit a beta particle, or sorry, an alpha particle. My number on the top is going to go down by 4. My number on the bottom will go down by 2. And if we look at who belongs to 90, we have thallium. So this would be the nuclear reaction that uranium-234 could undergo. In the next one, Z is equal to 33. Its atomic mass is 74.92. So when I look at the mass of 81 compared to 74.92, it is also much higher. So again, this one is going to be neutron rich, which means it's going to undergo beta decay. So when I write out my nuclear reaction, I'm going to kick off a beta particle. My number on the top stays the same. My number on the bottom has to go up by 1 so that they can add up to be equal. And when I look at who belongs to 32, we have germanium. Finally, when we look at D, the number of protons is equal to 57. And remember, when we have 57, an atom that has protons between 55 and 60, we like that N to Z ratio to be above 1.3. When I look at the atomic mass, it is 138.9. So the mass of this nuclide, 127, is much lower than the atomic mass. So in this case, it is going to be proton rich. And it will undergo beta emission or positron emission rather, or electron capture. So if we look at the positron emission, it's going to emit a positron. The number on the top will stay the same. The number on the bottom is going to decrease by 1. And when I look at who belongs to 56, we have barium. Now, if I look at the electron capture, I can do the same thing. I can start off the same way, but now I can do electron capture. So we'll capture that electron, and in doing so, we'll yield something on the other side that has the same mass number, and my number on the bottom has to go down by 1, and you'll notice that we yield the exact same thing. Barium 127.